and how to talk about future value with simple interest. And now in Section 5, what we want to do is to take a look at what happens if we have compound interest involved. So it's a little bit more of a realistic kind of approach. So in slide number 2, let's kind of outline what we want to do in this section. Um, First, we want to define what an annuity is. It's something that's kind of commonplace, and a lot of people invest in them now. Second, we want to be able to compute the future value of an annuity. And then third, we want to do just the opposite. We want to not only compute the future value, but given a future value, to find the payment of an annuity. That's called a sinking fund. And then finally, we want to be able to find the interest rate for an annuity. So in slide number 3, let's start out here and talk about what we really need to know to get through the content in this section. First, we can define an annuity as a sequence of equal periodic payments into an account. So sometimes people make payments into a savings account. That's a type of annuity. Sometimes people invest in the stock market with periodic payments. That's a type of an annuity. Some people also invest in insurance policies on a periodic basis. That's another kind of annuity. The interval between the payments is called the payment period. Normally, that's monthly for most people, but it can also be done annually or quarterly. Also, an ordinary annuity is an annuity where the payments are made at the end of each month. Now, those are the kind of annuities that we'll be talking about in this section. Ordinary annuities, and the payments are always made at the end of the month as opposed to the beginning of the month. All right, so in slide number 4 now, let's talk about the future value of an annuity. So let's go ahead and define that first. We can say the amount or future value of an annuity is the sum of all the payments that are put into that account plus all the interest earned on that account. So remember, not only are the payments going in there, the interest is accumulated on those payments. And since it's compound interest, we're also getting interest on the amount of compounding we've had prior to our periodic payment. Okay, so let's take a look at the formula for future value now. We can say if PMT represents the amount each payment is made at the end of the payment period, at the end of the month, that kind of thing. I is the interest rate per period. Then the future value, FV, after n payment periods, is given by the formula, so notice what we have here. The future value is equal to the payment amount times this fraction, which gives us the interest on that. So notice what we have here. We have 1 plus the periodic rate. So remember, that's the annual interest rate divided by the number of times we compound per year. That's I. And then we raise that to the n power. Remember what n is. N is the number of payments we make per year times the number of years. So for example, if we deposit monthly over 10 years, that would be 10 times 12, 120 payments. And then we want to take 1 away from that in the numerator. And then we divide that by the periodic interest rate. So let's take a look and see how we use this formula, and then we'll talk about how we can use our TVM solver and our calculator to help us out with some of this stuff. So in slide number 5, before we get to an example, let me just talk about some of the I guess the old style notation that's used in some more traditional style textbooks and some of the older textbooks. This angle notation. Some textbooks represent the fraction, excuse me, in the future value of an annuity formula with angle notation, similar to what we have shown on the slide there, where we have an S and then an N with a little angle. It's a straight line with another line going down, and then an I. S and then N angle I. All right. So what that does, it gives us a constant a multiplier to use to multiply by the payment, given the number of payments and given the periodic rate. So we really don't use this all that much anymore because, this would be a bunch of tables that would be in the back of our textbook. But because of our calculators now, we really don't need to use this angle notation anymore. Okay, so like I was saying earlier, let's go ahead and take a look at an example here. So in slide number 6, we have example 1. A Senate Office of Research Analysis estimates that California householders with gross incomes at or below $15,000 per year with one smoker spend an average of $870 per year on tobacco products. So what we're saying is, they found in California that among these people who make at or below $15,000 a year, they spend about $870 per year buying cigarettes and cigars and pipe tobacco, that kind of thing. It says here, if the annual amount were invested into a savings account earning 5.75% interest compounded annually, how much would be in that account after 25 years? So in other words, if instead of what we're trying to get to, instead of spending that money on tobacco products every year, that money was invested in an account for 25 years. The question is, how much would be in that account after 25 years? That account makes 5.75%, and it's only compounded annually. All right, so let's take a look and see how we do this now. First, let's understand the situation in slide number 7. We need to compute the future value. Remember that, so we're looking for FV here. The payment is, the PMT value is 870. K is 1. That's the number of payment periods per year. And remember, this interest is compounded annually. The number of payments is 25 times 1, or 25, compounded annually. And the periodic rate is 0.0575. That's our interest rate turned into a decimal, divided by 1 because we're compounding annually. So the periodic rate and the annual rate are exactly the same in this case. So notice here in the right column, we've went ahead and found the future value. That's $870, the annual payment, so to speak, the amount saved from not buying these tobacco products. And then in the numerator of our fraction, we have 1 plus 0.0575. That's our interest rate. And then we're raising that to the 25th power because that's the number of payments times the number of times each year we make that payment. So that's 25 times 1. And then in the numerator, we also subtract 1. And then in the denominator, we have our periodic rate. So notice here, if you compute that value, and let's go ahead and do that on our calculator here, just to kind of verify that we can do that. So let me grab my calculator. So that would be $870 times 1.0575. I just took the 1 and added it to the periodic rate. And then I guess we don't need the parentheses yet. Let me back up here. And then we want to raise that to the 25th power, the number of payments, minus 1. And then we're going to divide that by the periodic rate, which in this case is 0.0575. Hit the enter key, and notice here, I'm sorry about that. Let me go back and delete that parenthesis we didn't need. All right, let me hit the enter button. Now notice here we get the amount of $46,084, and rounded to the nearest penny, that would be 98 cents, wouldn't it? And that's exactly what we have here. So let's interpret the answer here. So this means that if a